are you and welcome to our show today. My name is Ted Mangrove. This is Physical Sciences Grade 10 Paper 1 revision for the second term. Now that we have reached the end of the second term, we just want to do a snapshot of quite a number of sections that we discussed in this quarter and try to guide each other in terms of the approach in answering some of these questions. So our session today is divided into two parts, which is the first one, which will be based on the techniques of responding to multiple choice problems, as well as looking at different structured questions that will be particularly in the section B. Let's hope we have an interesting session. It will be very critical today just to pay careful attention to the detail in terms of the approach. Let's look at the first set of questions, which is the multiple choice. I'll give you a chance at one time or the other just to attempt that. Let's also pay careful attention to the time management as well, which is something which we'll focus on today. Right. Okay, now if you look at the first question, which is a multiple choice, it says consider the circuit diagram below. So this is a circuit which is presented in terms of the symbols, right? It is represented in terms of the symbol. The light bulb are not necessarily identical. So we want to think of these light bulbs as resistors that have been connected in that way. It's very important to understand, okay, this is our battery, or which is a combination of cells, okay, and then that's our ammeter. Pay careful attention. It has been connected at a point which is in series. Very, very important, right? And then now these two light bulbs are connected in such a way that they are parallel, okay? So as you study carefully the diagram, very important to take note of those. The switch is closed. In other words, this is a complete circuit by the virtue of the fact that the switch is closed. So we want to think of this as a complete circuit, right? Because the switch is closed, right? Now, closed switch implies that the circuit is complete. Right. Now, having studied the diagram, let's look at what the questions are based on. The simple circuit, right? Now, if you look at, it says the reading on A2, just let's go back to the diagram. Now, where is our A2? Our A2 is this ammeter, which measures the current that goes, let's call this maybe resistor 1, and we call that resistor 2, right? So it simply means that all the current passes through A1. A1, we want to think of it as the I total, or the total current. But then this one, this is total current. It means, in other words, whatever A2 and A3 measure, it's with respect to the total current. So whatever total current we have is divided between these two because it's a typical example of a parallel circuit. Right. That said, let's look at the possible solutions. That says the reading on A1. Okay, we're talking about A2. It says it will be equal to the reading on A1. Remember, we said they are not necessarily identical, okay? So they are not necessarily identical, okay? Very key. Now, what is important as far as multiple choice is concerned is that of the four possible options that have been provided to us, only two of them more or less are relevant, and one of them is the most correct answer. The other two, we shall refer to them as distractors, okay? So in this case, because they are not necessarily identical, we would want to think of this one as a distractor. And then let's look at B, half the reading of A, okay? Because we're not given the magnitude, this cannot be entirely true. Now, if we know the fact that I total in this case is the current that goes to I2, or which is regulated by A2 plus, or in this case, okay, it has been labeled I1, okay, so I1 is equals to I2 plus I3. Why? Because current has been divided. Very key, current divided, because this is a parallel circuit, right? So it says we want A2. So in this case, if we go to A2, so the reading on A1 is equals to the reading on A2 plus the reading on, this should be 3, okay, on A3, right, because this is the total current. So if we want A2, it's a simple linear equation. We make A2 the subject. It means A1 minus A3 must give us A2, to show that the total current is split there or divided. So we look at something which speaks to this. In this case, the reading on A3 minus the reading on A1. Okay, or the reading on A1 minus the reading on A3. In this case, it should be A1 minus A3, not the other way, because A1 is the total current, right? Is the total current. So for that reason, D becomes our appropriate answer. So in this case, we need to emphasize on the technique that when you look at a question, you look at one possible answer at a time, but also bear in mind that you have to recall the key concepts that have to do with the question concerned. Right, let's look at the next one and see how we have understood the technique. Right, this one is based on sound, wave, and light. Very, very interesting section that we did. It says, consider the diagram of a wave. Why exactly do we call this a wave? Because it's a series of pulses, right? It's a series of pulses, right? So many pulses repeated with a frequency of 5 Hz. Okay. So now we are told that we've got this measurement, which is XY, right? So this is our rest position, okay? Rest or equilibrium position where the particle has experienced zero disturbance, right? So we are paying attention to X to Y. Okay, this is the dimensions, right? So now, having analyzed the question in that way, I think it's very important to also pay careful attention to the levels that are given. Say, for example, if we can just redraw that sketch, there were 2 complete pulses, right? So if, for argument's sake, this is our rest position, right? This is our rest position. So the dimensions that have been given in this case, that's point X, which is our crest, and point Y, which is our trough. So the perpendicular distance, which is from crest to the other trough. So this is our X and that's our Y. Now, that said, it's very important to understand that this is the point of maximum disturbance from rest position, yet this is another point of maximum disturbance from rest position. However, this is in the opposite direction from the one that moves from rest position to trough, the other one rest position to crest. So this is 2 times the amplitude, okay? Right. So if this is 2 times the amplitude, in other words, it says to us, indeed, this is twice the amplitude. So that's the technique as far as answering the question. Now let's look at further questions. I'll give you a chance to attempt that, all of them. I'll give you about a minute. I'll be flipping every 10-15 seconds, so just keep track of the time. Then after that, I'll try to consolidate. Right, starting from now, this is the first question that I would like you to attempt. It says 10 coulombs of charge passes through a point in a circuit in 2 minutes. The current in the circuit is, starting from now, I'll give you that time to attempt 2 minutes. Welcome back, guys. Hopefully you have made your attempt on the few questions on multiple choice that I just gave to you. Let's quickly have a feedback session in terms of what's the best approach to use, as well as to pay attention to, as well as the concepts that are related. Right. I'll just quickly go back to the first question. All right, it says 10 coulombs of charge. That's the quantity of charge. In other words, that's the value of Q, right? And then the time is in minutes. It means we have to change that to seconds, which is 2 multiplied by 60, which gives us what? 120 seconds. You need to have your calculator ready. Now we want to determine the current. So now we are given the time as well as the charge. So we know that I, which is current, is equals to quantity of charge that passes through a point per second, or rate of flow of charge. So in this case, what do we have? We've got 10 divided by 120. So our current in this case becomes, if you can quickly go to our calculator, right? If you can quickly go to the calculator, what do we have here? 10 divided by 120, right, which gives us exactly 1/12, which is our current in this case is 0.083 amperes. Remember, the units are very, very important. So the units are amperes in this case, right, which means in this case our solution is A. So based on the calculations there, right. Now, if you look at the next question, we've got electrostatics now, one of the interesting sections that we did quite a lot. So this is a physical process which has to do with what we referred to as contact, right? So during contact, particles share charge equally. So the following is correct? Which of the following is correct regarding the charge on each sphere after they are separated? So the principle of conservation of charge stipulates that the quantity of charge remains constant during a physical process as long as it's an isolated system. So we very much want to think of this as an isolated system, in the sense that these charges stand on what would refer to as insulators. So there's no more charge coming in or charge going out. So Q, which is charge on each sphere after separation, is the net charge. Net is the sum, which means, let's say this is Q1 and then this is our Q2, which becomes Q1 plus Q2 all over 2, right? So in this case, what do we have? We have 3 coulombs plus -4, okay, divided by 2, of which what we have then, the numerator is -1 divided by 2, which is -1 divided by 2, we get -0.5 coulombs each, right? So they have an equal charge. So when they are separated, each one of them will be -0.5 coulombs, -0.5 coulombs. Okay, so if you look at our answer, then it means C is the most appropriate answer in this case. So the calculations are very, very important, and also we need to refer to the formula sheet for some of the formulae that may always be given, like the one in the previous section for current, which is charge per unit time. So you use that formula correctly and do the calculations, and then you look at the answers, right? And then we go to the next question. Okay, we've done that. Okay, the last question, which is when the volume, which is a property of sound, right? Volume is a property of sound, okay, sound wave, and we know that sound waves are typical longitudinal wave. So in this case, we also have to be in a position to classify between longitudinal and distinguish rather between longitudinal as well as transverse wave. So sound is a typical example of a longitudinal wave. So in this case, the two properties, the other property is pitch. Okay, the other property is pitch. Okay, but in this case, they are dealing, the question specifically refers to volume. Volume is what sometimes you can refer to as loudness, right? It's something that we can refer to as loudness. So loudness can be divided into 2 categories: softer sound as well as a louder sound, right? Louder So these are the two extremes. So these have a lot to do with amplitude. Both of them are determined by amplitude. So that link of trying to establish that sound in terms of volume, it has to do with amplitude. So in this case, we look at the one that has to do with amplitude. Obviously, C is the one. But remember that pitch has to do with frequency. Okay, or wavelength, because frequency and wavelength are related. Right. That said, this brings us to the end of the first segment of multiple choice. We shall talk a short breather. Then after that, when we come back, we shall look at more structured questions. Let's take a break for now. See you after the break, guys. Welcome, guys. After our short break, hopefully you have taken the much needed research. For now, let's look at the structured questions as I indicated earlier on. Right. It says here a context. It's very important for us to read. It says grade 10 learners, that's yourself, set up the following circuit. Circuit. Remember, in this case, we use the symbols to show the circuit, consisting of two resistors. There are two resistors connected in series. Series has been put in bold there. You know that series, it means that there is only one path for current to flow, right? To a battery, there's a 3-volt battery there, right? And then in the switch, which is already closed, as we have seen in the multiple choice. An ammeter, which is a device, is connected in series. So connected in series at a point, very important, at a point. So in other words, it will determine how much charge passes through this point per second. And the voltmeter connected over the first resistor. What is very important about the voltmeter is that it's connected across R1. So it will measure the work done across R1. We can call it V1 if we like, so that we know it has to do with R1. Okay, so R1 and R2 are connected in series. So whatever current passes through the ammeter will pass through R1 as well as R2, because this is a typical series circuit. Right, let's go further and check what it says. Okay, when the learners connect the circuit, they get a reading of 1,5 amperes. So in this case, this 1,5 amperes is the one that is on the ammeter. In this case, we can think of the total current in this case as 1,5 amperes, while the voltage from the source in this case is and the 2 volt and is 3 volts, right? So this is V total, okay, from the source, which is the cell in this case, not a battery, because it consists of one cell, right? Calculate the amount of charge passing through the ammeter in 10 seconds. We have seen this before. We're going to our formula sheet. We know that I is equals to Q over delta T. In this case, the quantity of charge is what we're looking for, right? So in this case, we copy the formula as is from the formula sheet. Then we have the current. It means the current is 1,5 is equals to Q divided by the time, which is 10. So if we make Q the subject, we'll get Q is equals to 10 multiplied by 1,5, right? So whatever we're going to get is going to be coulombs, because we're talking about the charge. So Q becomes, in this case, 15 coulombs. It's just multiplication there. So this is how we would attempt this particular problem. Now, the follow-up question on the same circuit says, on the same circuit, right, let me check. Okay. Right, now calculate the resistance. Calculate the resistance of this entire circuit. Now we're talking about the equivalent resistance. If we were going to take the two resistors and represent them as a single resistor, what resistance would it have? That's what we talk about when we talk about the total or the equivalent resistance in a circuit. However, this is a series circuit, remember, very, very important. The other type of circuit or connection is a parallel. So we know that the R total in a series circuit, in this case, will be R1 plus R2. If there were more of them, it would be plus R3 and so forth until Rn resistors, right, that are connected in series. But we know that in a series, only one path for current, to flow. Very, very important. One path for current flow, right? So in other words, whatever current goes through R1 will go through R2. But in this case, the question wants us to calculate the total resistance. So the combined effective resistance of the two resistors will be, we need to go back to that. Will be in this case V total, in this case over R total, right? Okay. Now, in this case, this R total is a result of these two resistors put together. So we're looking for R total. So V total, we know that it's 3 volts. Okay, this is supposed to be I, right? Because it can't divide by, this is I total, right? So it's 3 divided by 1,5, which is exactly 2 ohms. So the combined resistance of the two resistors in this case is 2 ohms, right? We don't know whether they are equivalent or not because the question did not specify that. So in this case, if we go further, again it's the same. So the combined resistance of these two resistors gives us exactly 2 ohms, 2 ohms, right? And then this ammeter is the total current is 1.5 amperes, right? That's what we know by now. And then it says here, this is in terms of classification. Yours is to choose correctly, but as you choose, you need to pay careful attention to the concept under concern. In this case, we're talking about a series circuit. We know what happens to current. You know, whatever current goes through R1 would also go through R2. So hence we say in any series circuit, current remains constant, yet voltage will be divided, right? So in other words, we would say that resistors in series are potential dividers. What do we mean by potential dividers? If we can go back to that circuit, okay, right? So we knew that we are told that this one is 2 volts. Okay, V1 is 2 volts. So in other words, if we had connected another voltmeter across R2, that is between 2 points across R2, let's call it V2, right? So in other words, we're saying that V1 plus V2 must be equals to our V total, which is 3 volts in this case. This must be V total. So in other words, we can tell that the same current goes through R1 as well as R2. But now because these two have got unequal resistances in terms of magnitude, so if this one is 2 volts, this one must be 1 volt, so that the total of the two gives us exactly the total voltage. Hence we say that any series circuit is a potential divider. PD is divided in a typical divided, okay, divided, okay. PD is divided, right, in any series circuit, because there's a series circuit, right? Okay, that's it. Let's go to the next question, right? Still the same circuit. Right now, if you check here, it says if the resistance of R1 is that, we're given the resistance of R1, explain how learners could calculate the resistance of R2 without the use of the Ohm's law. This is a fact that we have established, that V total is equals to V1 plus V2, right? So that's why, which explains why potential difference is divided. So how we need to explain how exactly we would calculate the resistance of R2. So if we have the resistance of R1, it's easy in this case that if we get the voltage across, we can use even ratio, because the higher the resistance, the higher the voltage across. Is it fine? So we can use the value of V2. So we know that V2 is 1 volt, right? So this 1 volt is when we add it to the 2 volts for V1, we get our 3 volts, which is the total voltage. So sometimes we may use the ratio, even sometimes we may use the Ohm's law, but the question says to us that without the use of the Ohm's law, we know that the point that is very, very important is that voltage is divided, not necessarily equal, is divided proportionally, is divided proportionally, right? So if it's divided proportionally, what are we saying? We are saying the higher the voltage, the higher resistance. In other words, voltage is directly proportional to resistance, provided that current is what? Is constant, right? Because this is a series circuit. So this will be only true if current remains constant. Very, very important for us to realize that fact. So in this case, because we've subtracted the 1 volt, so from that, we know that if 2 volts, let's say if we use the ratio, it says 2 volts is proportional, produces is to, we can say 2 volts is to 1,33, which is the resistance of R1. 2 volts is to 1,33 ohms, and then 1 volt would be, let's say, let it be X, right? So this is double, this is half. It means the resistance of R2 in this case would be 1,33 divided by 2. In this case, if you go to your calculator, just to determine the resistance, there it will be, in this case, what do we have? We have 1,33 divided by 2, okay, which is exactly 0.665 ohms. That's exactly the resistance without using the Ohm's law, by using ratio and proportion, because we said resistance is divided proportionally. Very, very important, right? Let's look at the next question. In this case, we're still in the same circuit, right? Let's look at, it says, how much energy is transferred through R2 in 5 minutes, right? Now, when we talk about energy, it has to do with work done. Now, let's remember the fact that a resistor is that kind of an electrical component that transforms electrical energy into any other form. It could be a light bulb, which will transform electrical energy into heat. As it does energy transformation, or as energy transformation occurs, work is being done, right? So we know that V is equals to work done, or energy transferred per coulomb of charge. But at the same time, we know that I is equals to Q over delta T, right? So that said, it simply means that if you make Q the subject here, Q is equals to, in this case, Q is equals to I delta T, okay? Having made the subject, so it means V will be equals to work, or energy transfer, over current multiplied by delta T, right? So if we make W the subject, it means work or energy transferred will be equals to voltage multiplied by current multiplied by the time, right? That said, then we would do obviously our substitution, which leaves us with W is equals to V. In this case, how much R2? We have R2 now. The value of R2, if you can check it from the calculator, 0.665, right? So it's that's the resistance. So it's 1 volt, okay, multiplied by the current, which is constant, 1,5, multiplied by 5, multiplied by 60, because we're talking second, the SI units of time. So work or energy transferred in this case will be, right, let's go to our calculator, right? So what do we have here? We've got 1 times 1,5, which is 1 times 1,5 times 5 times 60, okay, times 60 there. Okay, what do we get? We get 450. Because it's energy, it will be measured in joules, right? So basically, that's what is happening as far as that circuit is concerned, right? Let's look at the next question, which I'll give you a chance to attempt, right? Now, this is the sketch that you have. It's on sound wave and light. We've been exposed to this before. I'll give you a minute to try and look into that, and then we'll do the feedback. Starting from now, keep track of the time. Let's try it and attempt. I'll be flipping after 5 or 10 seconds, depending on the level of complexity of the question. Starting from now, let's try and attempt this question. welcome back, guys. Hopefully you have made your attempt on the question. Let's quickly sum it up on this very straightforward question on waves in terms of transverse, because these are typical transverse waves, right? Okay, let's go to the question, the first one. Right, it starts here, right here. So we're given three waves in this case, but we want to know the one with the greatest amplitude. Very important. Amplitude is the maximum disturbance from rest position. The distance or maximum, the distance of maximum disturbance. Okay, distance of maximum disturbance from rest position. Right. Right, so it could be from rest position to crest, rest position to top. So now we want the greatest. So this is the amplitude of wave 1. This is the amplitude of wave 2. This will be the amplitude of wave 3. So these boxes have been created such that we can easily count. So obviously wave 2 has the greatest amplitude. Wave 2, right? Why do we say wave 2? Because it's 1, 2, 3, 4 units, which is 4 units, right? Units. Whereas this one is 2 units, 2 units amplitude, okay? And then this one is 4 units, right? And then this one is also 2 units. So you realize that wave 1 and wave 3 have got the same amplitude. That's what is similar between the two, right? Let's look at the second one, which sketches the shortest wavelength. We know that wavelength, lambda, is the distance between two consecutive points in phase. Distance between two consecutive points in phase. Consecutive points in phase. Now this could be a crest and a crest and a trough and a trough that are one after the other. So this point is in phase with that point. So if we can think of it, this is our wavelength of wave 1. Okay, this will be our wavelength of wave 2. Okay, and then this will be our wavelength of wave 3, right? That said, I think it's easier to calculate or just to count 1, 2, 3, 4, 5, 6, 7, 8. So this is 8 units, okay? Our wavelength is 8 units, so that's our lambda 1, okay? Now lambda 2, in this case, is the wavelength 1, 2, 3, 4, 5, 6, 7, 8, right? This is 8 units, okay? Okay, which is equal to that of wave 1. So lambda 3 is 1, 2, 3, 4, which is equals to 4 units. Now this is actually half the wavelength of the other two waves. So for that reason, we can safely say that the one that has got the shortest wavelength in this case is wave 3. And I want you to realize that the one that has got the shortest wavelength has got the highest frequency. So this is shorter wavelength means higher frequency. Okay, short lambda translates to a high frequency, and we think of frequency as the number of pulses that are completed per second. So if you check, if these were propagated in the same time, would say that this one is 1, 2, 3. This one is 1.5. This one is 1.5. That's why these two have got the same wavelength. Then they've got the same frequency, right? Now the last question on this segment would be this one, which is to describe how the wavelength will be affected if period was doubled. So what is this period? Period is the t, time taken to complete a single pulse. So if we want to, if we doubled the period, it means if this is completed in 1, so it means this must only be half of the pulse. So seemingly then it means it will be like that. Okay, so once you complete 1, in this case you complete half, it means we didn't even change the amplitude, we only changed the period. So if we in this case the period is doubled, it means also wavelength will also be doubled. That's also what it means. So wavelength will also will be doubled, because if in 1 we complete half a pulse, it means it will take double the time again. right? So the wavelength will be doubled. It will be 2 times longer because it's length, right? Then the last question is which one of the following is the transverse wave? Remember, a transverse wave is that wave whereby the pulses are perpendicular. The disturbance is perpendicular meaning at an angle of 90 degrees, perpendicular to the direction of movement, that gives us what we call a transverse wave or motion, right? Movement or motion. So in this case, transverse is it's light, because it's not sound. Sound is longitudinal. So this is transverse. So light will be a typical transverse wave, right? Very, very key. Transverse wave. Okay. Right, now this brings us to the end of our second segment. We shall take a short break, and then after that we'll try and look at further questions where also you'd be given a chance to attempt a few, but very important to emphasize on the speed and accuracy in terms of managing your time. We shall take a break for now. See you after the break, good people. Welcome back to our last segment on today's revision, Physical Sciences, Paper 1. Emphasis has been made on the use of the formulae, the approach in terms of answering the multiple choice, and also paying careful attention to detail as far as what I would refer to as a catch in a question. Very, very important to stay focused in that way. In this case, it says a photon, okay, of orange light. Okay, this obviously is visible light. Okay, remember the visible light is part of the visible range of the electromagnetic spectrum. So the one that we refer to as the Roy G BIV, Roy G B. So it means from red to violet, right? So orange, there we are as far as orange. Okay, that's our orange there in the visible range of the spectrum. So we are given the frequency in hertz, right? So the first part is to define what we call a photon. The word photon means light. Right. So when we talk of a photon, we're talking about small particles that carry light energy. Small particles of light energy. Small particles of light energy. Right. We call them photons. So this energy can be determined using the formula E is equals to H multiplied by the Planck's, which is E is equals to the Planck's constant multiplied by the frequency. In other words, because this is a constant, the Planck's constant, we also must know that the energy that the photons or these particles of light carry are directly proportional to the frequency. In other words, the higher the frequency of the photon, the greater the energy that the photon carries. Right. So if we go back to our formula, which will be given, right? So energy of photon is equals to Planck's constant 6,63, always given, times 10 exponent negative 34, right? Multiplied by the frequency, which is 4.92, right? Times 10 exponent 14, right? So we multiply them. So E is equals to, use your calculator. I want you to watch carefully, because when it comes to scientific notation, it becomes a problem for many learners. Then what do we have? The Planck's constant, 6.63. So this is the key that we use to show that we want to use the scientific notation. So it's the negative, not the other negative. Okay, the negative for the sign, 34. We multiply that. We can open brackets as I've done in my substitution, 4,92, right? 10 exponent. In this case, it's 14, positive 14. We close the bracket, right? So our solution to this becomes 3,26, right? We two decimal places times 10 exponent negative 19. So energy is measured in joules. So this is the energy that each photon of this form of electromagnetic radiation carries. Now it says in short, that's what it means, in short. Hence, I want to emphasize at this point in time that if we're going to explain something, using scientific principles or scientific concept, it's very key that we only make mention of the scientific facts, because that's what carries the marks at the end of the day. Hence, at times, I want to encourage learners to use point form, instead of writing an essay. You may write a long essay, but with only one scientific fact. It means you'd also earn a mark for that, for so much work that we've done. Hence, emphasis is on the brief explanation, how electromagnetic waves are propagated. It's very important when we talk about electromagnetic waves. These are special waves which can be transmitted in a vacuum. So what we have is we need to have an oscillating charge, right, for us to propagate any form of electromagnetic radiation. We have an oscillating charge. So that oscillating charge, you want to think of it maybe as the electron, which creates an electric field. Okay, because it's moving, that it creates an electric field, right? Now, as long as there is moving charge, as you learn in later stages in grade 11 and 12, that if you have an oscillating charge which creates or generates an electric field, it also creates a magnetic field, right? A magnetic field. So in other words, what happens in this case is that the electromagnetic radiation is self-propagating. So because of an oscillating charge which creates a magnetic field and a magnetic as well as an electric field, these two are actually perpendicular to each other, right? Perpendicular to each other. So very, very important. Now, this can also be transmitted in a vacuum, that is in an empty space. In other words, what we're saying is that any form of electromagnetic radiation which is self-propagating can actually be transmitted in an empty space, okay, at a constant speed of 3 times 10 exponent 8, right, meters per second, right? So this is a very special property of electromagnetic waves, because this is the C, which is also a constant, which is 3 times 10 exponent 8. Right. Now, furthermore, it says, we've already attempted this. We've briefly explained how these are formed. Right. Now, if we can say maybe for a minute, attempt the following questions. 2 minutes will do, I think, because there are a few of them. It's just to do with basic recall. If you name it, you just list those, right? So I'll give you 2 minutes just to attempt this, and then we'll consolidate this question very quickly and sum it up for the day. Right, let's go for it, starting from now. Welcome back, guys. Hopefully you've made your attempt on the very few questions in the last part of our session today. Right. It says here, name in order of increasing frequency. In order of increasing frequency. So this has to do with the electromagnetic spectrum. So we've got the radio waves, right? This is the first one. Also, we have the microwaves, okay? Which means this one is the lowest frequency. Microwaves, okay? From microwaves, you've got infrared, okay? Infrared, right? Radiation. From infrared, we've got visible light, which consists of the 7 colors of the spectrum. The RGB, we've spoken about that. Then we've got the ultraviolet. After the ultraviolet, we've got the X-rays, right? Okay. And then we've got the gamma rays, right? Now, this is the full range of the electromagnetic spectrum. Give 2 types that have got the highest penetrating ability. Penetrating ability has to do with the energy, and we know that energy is directly proportional to frequency. So the ones that have got higher frequency would actually have higher energy, and in turn, they would also have high penetrating ability. So in this case is the X-rays as well as and the gamma rays. Okay, so that's the gamma rays there. Okay. So that's the symbol for gamma there, the Greek alphabet, right? Now, which 2 properties do all waves have in common in all sections? Now, this means that they can travel in an empty space, they are self-propagating, okay? Then also they are transverse, okay? Self-propagating transverse wave, and also travel in a vacuum. They can be travel in a vacuum, in empty space, right? At a speed of 3 times 10 meters, 10 exponent 8 meters per second. That's what we know about them. Name any 2 properties which differ in the section. So there is a lot that we can say as far as the properties. We can talk about the penetrating ability, okay? It differs, okay? Which depends on the energy, which depends on the frequency. Penetrating ability, okay? Also we can talk about the wavelength, okay? We can also talk about the frequency, right, of electromagnetic waves, right? So we can also talk about those 3. So any one of those 2, it varies. So from radio to gamma, we've got an increasing frequency, as we have suggested, meaning that wavelength gets shorter and shorter as you move from radio to gamma rays, right? And also penetrating ability increases across from radio to gamma rays. Basically, this is what we had for today because of the time constraints, but there's quite a lot that we still need to prepare on just to get ready ourselves for the June examination. Okay, guys, I think this brings us to the end of our session today. I wish you all the best with the June examinations. From myself, Temba Ngube, we shall call it a day for now. Goodbye and cheers. See you next time, guys.